So in this problem, a driver is traveling at a speed of 72 kilometers per hour in car A. When he looks down to text a friend that he is running late, just before he looks down, he is 80 meters from the intersection, and a bicyclist B, traveling at a constant speed of 8 meters per second, is 32 meters from that same intersection. The light turns red during the 3-second text, and when the driver looks up, he hits the brakes, causing a constant deceleration of 5 meters per second squared. Determine A, the distance between the car and the bike when the bike reaches the center of the intersection. B, the velocity that the car appears to have to the cyclist at this time. And C, where the car stops. So, part A of this question, which we'll begin with, is to determine the distance between the car and the bike when the bike reaches the center of the intersection. So the first thing that I suggest we try to find is how long it takes the bike to reach the center of the intersection. Now the bike is neither accelerating nor decelerating. It's traveling at a constant velocity of 8 meters per second. So the velocity of B, the biker, is 8 meters per second. Now, the time it takes the bike to reach the center of the intersection, which is 32 meters away, is the distance traveled by the bike, that would be the 32 meters, divided by the velocity of the bike. So 32 over 8 is 4 seconds. So it takes 4 seconds for the bike to travel the 32 meters to the center of the intersection. So now the question that we need to answer is, after that 4 seconds, where is the car located? How far did the car travel after that 4 seconds? So, as far as the car is concerned, we need to break its kinematics up into 2 different sections. We need to consider the first part, the first 3 seconds, where the driver is looking at their text and they're traveling at a constant speed of 72 kilometers per hour. So the velocity of A is 72 kilometers per hour, and I divide this by 3.6 to convert it to 20 meters per second. In that first 3 seconds while the driver is looking at their text, the distance traveled is the velocity of the car times the time, so that would be the 20 meters per second times the 3 seconds, and that equals 60 meters. So the car travels a distance of 60 meters in the first 3 seconds. Next, we need to figure out what happens in the final second, because we're considering a total time of 4 seconds. So in that final second, the car is slowing down, decelerating, by 5 meters per second squared. So the distance traveled by the car in that time is equal to v0t, the initial velocity of the car times time, minus 1/2 at squared. So in our case, that's going to be the 20 meters per second, that's the initial velocity, times 1 second minus 1/2 5 times the time, 1 second squared. And when you work this out, you get 17.5 meters. So in that 1 second interval during which the car is decelerating, the car travels a distance of 17.5 meters. So the total distance traveled, I'll call that d total, for the total distance traveled by the car will be the 60 meters that occurred in the first 3 seconds while the driver was looking at the text, plus the 17.5 meters from that final second where the car is decelerating, and that gives me a total distance traveled of 77.5 meters. Now the question asks, how far is the car from the intersection? Well, the car starts out a distance of 80 meters from the intersection, so the distance to the intersection is the total initial distance, 80 meters, minus the distance traveled during those 4 seconds, and that distance is going to be 12.5 meters. So that is the answer to part A. Part B. Part B asks to find the velocity that the car appears to have to the cyclist at this time. So the question is, at this time of 4 seconds, this is the time where the cyclist is at the center of the intersection and the car is 12.5 meters from the intersection. At that instant, what is the velocity of the cyclist? What is the velocity of the car as seen by the cyclist? What we want to find here is the velocity of A with respect to B. This is a vector quantity, and it's defined as the velocity of A, which in our case is the car, minus the velocity of B, which in our case is the bicyclist. The velocity of A is the velocity of the car at the time when it's 12.5 meters away. In other words, at a time of 4 seconds. So first we need to find that velocity. So the velocity of the car equals the initial velocity minus the deceleration times time. So this is 20 meters per second minus 5 meters per second squared times 1 second equals 15 meters per second. This is the velocity of the car at a time of 4 seconds. Remember, the first 3 seconds, the car just has a constant velocity, v0. It's during that last second where the car slows down from that 20 meters per second down to that 15 meters per second. So that's the velocity of the car. If we want to write this as a vector, we call this v sub a. That's the velocity of the car. The car was called particle A. It's 15 j hat. J hat represents a direction in the y in the y direction. Next, we need the velocity of the cyclist. Now, in order to determine the velocity of the cyclist, we need to do some trigonometry here. So remember, this cyclist is traveling at 8 meters per second at a particular angle. And in order to characterize the angle, let me first point out that we are given that this angle here is 110 degrees. So this angle is 110. That means that this angle is also 110 degrees. The angle that the bicyclist makes with the horizontal, here is the horizontal in blue, it is this angle right here that the bicyclist makes with the horizontal. And this angle right here will be 110 degrees minus 90 degrees, which is 20 degrees. Remember, the horizontal is perpendicular to this here, so we take 110 and subtract 90 degrees in order to get 20 degrees. So in summary, what we have is the cyclist is traveling at 8 meters per second at an angle of 20 degrees with respect to the horizontal. That means the x or horizontal component of the velocity will be 8 times the cosine of 20, and the y component of the velocity will be 8 times the sine of 20 degrees. So now we can use that information to put together the velocity vector for the cyclist. So in this case, the velocity vector v sub b will equal 8 times the cosine of 20 degrees I hat minus 8 times the sine of 20 degrees j hat. We have the minus sign there because the y component of the bicyclist's velocity is downwards. So now that we have the velocity of A and the velocity of B, we could form the velocity of A slash B. That's 15j hat minus 8 cosine 20 I hat plus, notice the sign has changed because you distribute the minus sign, plus 8 sine of 20 j hat. So we can combine the j hat terms with the I hat terms. There's only one I hat term. So the 8 cosine 20, that's equal to 7.52. So we have minus 7.52 I hat. And then we have plus the 15 plus the 8 sine of 20, that works out to 1774. It's in the y direction, j hat. So that's the final velocity, v sub ab. That's the velocity that the bicyclist perceives the car as having in their reference frame. Now we come to the last part, which is part C. Part C says to find where the car stops. So we want to find at what position the car stops. The way I approach this problem is first I determine how long it takes the car to stop. So remember, what is the car doing? The first 3 seconds of the car's motion is just at a constant velocity. It travels 60 meters. After that 3 seconds, the car decelerates, and it goes from 20 meters per second down to 0 meters per second. So the question is, how long does that take? Well, to figure that out, we use that the velocity of the car, we can go to whatever the final velocity of the car is, equals v0 minus at. So we want to find the time when the car comes to rest. So we put a 0 there. 0 equals 20 minus 5 times t. We can now solve this, and we find that t equals 4 seconds. So it takes 4 seconds for the car to come from rest after it starts slowing down. Of course, the total time the car is driving for in this scenario is 7 seconds. So now the question is, what is the distance traveled in that final 4 seconds? Well, the distance traveled by the car is v0t minus 1/2 at squared. So that would be the 20 meters per second times 4 seconds minus 1/2 times 5 meters per second squared times 4 seconds squared. And when you work this out, I find that I get 40 meters. So the total distance traveled by the car will be the 60 meters that's traveled during the first 3 seconds. This is the 3 seconds where the driver is looking at the text. So it's the 60 meters plus the 40 meters. This is the distance traveled as the car slows down when they step on the brakes. So the total distance traveled is 100 meters.